Right, welcome. So my name is Adib. I'm currently an applied machine learning intern at Vector. I was previously at Borealis AI and Intern doing some cool other AI research. And I'm currently a student at University of Toronto majoring in computer science and neuroscience. Now, the goal of the project today, which we named the Project Odyssey, is to use electronic health records. As you know, electronic health records is an abandoned form of patient information from physician diagnosis, medication, lab results, any sort of observation that happens during hospital visits across time, and it provides a rich source of information about your patient. Now, given an electronic health record, you know everything about that patient. So if you could feed that to a machine learning model, you can ask that model to predict what is the chance of my patient dying in next month after post-hospital discharge, or what is the chance of developing cancer. And your model is able to predict that with a high accuracy because it knows every single medical information that has happened for that patient through time. So the goal of our project is to create such foundation model using machine learning on this data and showcase its interpretability as well as its achievements on different various fine-tuning tasks, such as mortality prediction. Our data is comprised of about 200,000 patients from the famous MIMIC IV dataset, and we use a standard FHIR format, which is a generalization of how you might represent different observations, different lab results, different medications, such that you could generalize to different hospitals, because now any concept you have about what type of diagnosis has been diagnosed is the same across patients. For this specific model, we use only medications, which are types of drugs that's been administered, lab tests, such as your blood glucose level, and procedures, such as any type of surgery that has happened. Now, given this data, we need to somewhat represent it over time. You need to know what has been the exact details of each visit, what was the age of the patient, and all this different information. And I know this diagram seems like a really messy piece of information that you want to just feed into your model without knowing what it does. But we'll go through it to understand how exactly we feed all this information. So let's say we have an English example. We say, hi, my name is Adib, right? These are represented as different words after another, and it captures a meaning, such as me explaining my name. Now, what if we could do the same thing with all these labs and medication and these types of information? In order to do that, for any of these ideas, represent a single word. Let's say a single word represents you have diabetes. A single word you have high blood glucose. And these are in different categories. It could be a medication, a procedure. And now we stack them one after another based on distance. So we say, let's start. We put a VS word representing the start of a visit. And then we say we had P1, which represents one procedure. Maybe you had a part of your body diagnosed. M1 and M2 becomes medications. You had this other medical like dropping or any other thing administered, and then visit end, you ended that visit, some amount of time passed, like 2 weeks, and then you have again another visit, and so on and so forth. And by this representation, we showcase what is exactly the details of different medical ideas through time. Adding to that, we also represent the age of the patient, the timing of these actions, as well as what was the order that these events happened. And we fit all of that as a compressed sequence of words to our model. In other words, your model is seeing the patient through time with every single thing that happened in each single visit. Now, how do we train a model on top of this data? Fortunately, we have great NLP engineers focused on developing models in English language. And since we're building a model that can use that same sequence, we can replicate their work. We use the model, the transformer model, which is at heart of many of the language modeling different tasks. And the way it works is you will pass on your sequence of words down here. We have CLS, the start, visit start, the first procedure. But then we'll say, I'm not going to give you the next word in the sequence. And what you need to do is you have to predict what was here. This will help the model to learn what is a general sequence look like. If you have start of the visit, or maybe if you have these types of medications, you'll end up having these types of procedures. And so overall, your model will learn how the patient progresses through their journeys over different visits. After you have this model settled, you will use the same thing, but now you will ask it to predict if the patient is going to die in the next month or not. Now, since the model knows and has seen many different patients dying or not dying based on different procedures and medications that happen to them, it's not able to do it accurately for your new given example. Another model we also use as a baseline type of comparison is called an XGBoost. And an XGBoost model doesn't really care about what is the sequence of things that happen, and mostly cares about what are the things that happen. I don't care when you had your medication, I just care if you had that medication or not. And it uses those information to predict, oh, maybe you had too many medications related to glucose, maybe you have diabetes. And we use these two models in different mortality or other types of healthcare tasks. For example, you'll see an impressive 90% accuracy on predicting the chance of death within 1 month since hospital release. And this is an impressive result, which means your model is able to accurately predict. And so you as a hospital probably shouldn't let that patient go if you see a high chance of death. And the same thing also happens with some other tasks. For readmission, the chance of predicting if the patient will be readmitted to the hospital within 1 month is again pretty high with our model. And you can also see the same thing with predicting conditions, such as what is the chance of having kidney failure based on the types of medications and different procedures I'm seeing in this patient. So this model opens the door into predicting a lot of the important ideas we need about a patient and using that to have better actions that we take for our patients. Again, with all these models, there are black boxes. So you at least want to get an idea of how they're making their predictions such that you're able to better understand the underlying mechanisms. Here is the given patient that we had been seeing before. It starts with CLS, visit start. These are all different concepts that happen, like labs, etc. And then it ends with that visit. Now we can see here that our model was paying a lot of attention to this specific 17th token in our sequence. And this is, without a doubt, actually a lab result that shows you have a high amount of protein in your urine, which is usually an indication of kidney failure. And then you can see how things coincide. The model that's predicting kidney failure is also paying attention to a type of lab result that we usually, as doctors, coincided with having kidney failure. Another way you can interpret it is by looking at which of the features that we fit in, such as labs or medications, are important. And you'll see usually the lab are the most important part for that given patient. And as you can guess, if you have a lab result that shows presence of a symptom, that's an easy way to also diagnose what condition the patient has. And some of the novelties our model has. One of them is, if you think about it, a patient will have hundreds and thousands of different events that happen through these visits. If you're living for 50 years and you go to hospital, it's going to just accumulate. So you need a model that can feed in all this vast majority of data and be able to process it. And for the first time, we actually use a type of transformer called the Big Bird model, which is able to increase the context length, the length that you can fit into your model, up to 4 times the current state-of-the-art models, which is the longest reported. We've also open sourced this model in our GitHub repository, so any researcher can not only build on top of our code, but also directly use it for their own specific tasks. And as mentioned, we use the FHIR resource format, which is the most standard, popular open format, which allows us to be used in that model in different hospitals and in different settings. Recently, we also developed a version of our model that can predict all these different mortality and different various diagnoses in a single go, which enables us to use only one model to get everything done. What are the challenges associated? One of the main ones is getting all this data, processing them, putting everything together, making sure the model works. Compute is one of the main constraints. If you have hundreds of thousands of patients, you need enormous GPUs to be able to handle that. And most importantly, can you generalize and also be interpretable based on the decisions you're making? And our next steps are actually using other data formats, such as the GEMINI data, which is a Canadian-specific data set of over 30 hospitals, using modalities such as images, even increasing the content length beyond what we already have achieved, and of course, submitting it to NeurIPS for a chance to get publication. And yes, that's all. Thank you.
Questions? I'm curious, like on the data curation side, like I know even within Mimic, and especially when you're talking about exploring other data sources, that there's like a potential for, some hospitals may not have certain features or lab results. How much did you kind of face that when you were like kind of processing the Mimic data set, and how do you think that's going to play into kind of when you try to include future, health-related data sources?
Yeah, that's a great question. Actually, the FHIR format we discussed has 30 and even more types of information, not just observations and medications, but a lot of other things. And many of the reasons we don't use those is it might not be available across hospitals. So in general, the lab results, the medications are mostly widespread use across hospitals. So you can expect those to be present, but other types of modalities might not be available And for this proof of concept, we actually use only the ones that are available. And we are also going to be using the same things in the GEMINI data. And we believe that these three major sources, that the medication, the labs, and the procedures, incorporate the majority of what goes on in a hospital visit and allows us to be able to predict well for these different fine-tuning tasks discussed.
Yes, I have a question for you. So while working on Project Odyssey, we'd love to know if there was any major bottleneck you came across and how you resolved that problem, if you were able to do it.
Oh, definitely. The major challenge that we had at first was the length of the patient. We were originally using a 512 number of tokens, and that's not enough to capture the majority of things that goes on in tens of different visits. But if you use the traditional transformers and let's say instead of passing 512, you pass on 4 times that amount of input, the model is not able to learn well because of the memory requirements. So we had to use a specific set of transformer models that do their job differently and in a more optimized way. And the technical term is, in a transformer, each of the words you have, let's say the word that represents high blood glucose, we look at all the other words in your sequence to understand its role. For example, we'll end up looking at the diagnosis for diabetes in your sequence, and it will understand, oh, that's why I'm correlated with diabetes. And if you have 2048 words, it becomes a lot of people paying attention to a lot of people, so you won't have enough memory for it. And what the Big Bird model does is it says, instead of paying attention to everyone, just pay attention to your neighbors and some couple people you know and some random people. And hopefully, if you know my friend who knows your friend, we know each other. And that's how it's able to do its job.